First, I'd like to introduce the Meteor project, which enabled the creation of this video. Meteor stands for the Modelling Exposure through Earth Observation Routines and was funded by the UK Space Agency through their International Partnership Programme as part of the Global Challenges Research Fund. The Meteor project aims to develop innovative application of Earth observation technologies to improve understanding of exposure. Natural hazards have had escalating impacts, which are contributed by an increasing exposure of population and assets. However, a major challenge when making disaster risk management decisions can be a poor understanding of the distribution and character of exposure. Robust quantitative methods are required to justify these decisions, and in this project we are looking at the use of Earth observation technologies within that context. Within the Meteor project there is also the aim to share knowledge. This video is produced as part of a series of educational videos to enable the use of Meteor products and data. In this introduction to landslides, I'm going to cover what is a landslide, how a landslide is classified, covering different classification schemes. I'm going to give a few examples of landslides, moving on to what causes landslides, and then how landslides can be captured in landslide inventories, and then how these landslide inventories can be used to produce landslide susceptibility maps, and the different techniques that can be used, and the considerations before choosing your technique. So, what is a landslide? So, landslide is an umbrella term that covers a wide variety of processes, but simply put, it is a type of mass wasting, commonly defined as a downslope movement of soil and rock under the influence of gravity. There are a number of definitions used in the literature, but this one by Cruden is often quoted. The block diagram on the left shows a range of geological and geomorphological settings that are subject to landslides. So we have our high mountains, our submarine slopes, as well as our coastal cliffs. A number of different types of landslides are shown. We have rock falls, we have debris flows, we have rock slides, and we have riverbank collapses. We also have rock landslides and soil landslides. All of these are captured by the term landslide, but this variation shown highlights the need for a classification scheme so that all these different types of movement and processes are clear. Classification schemes help us to use a common language to be able to effectively communicate the process we are referring to. It provides internationally recognised terminology. Landslides can be classified by the type of movement, the rate of movement, so speed or velocity, and the age or activity of movement. And this diversity of classification reflects the diversity of processes that we saw in the previous block diagram. There are a number of classification schemes in the literature, including Varnes, Hunger, and Sharp, and they are all subtly different. Hunger recently built on the commonly used Varnes definition scheme. This is a relatively simple classification scheme based on type of movement, showing 5 main types. We have 4 in the top left, where material is detached from a cliff or steep slope, and then rolls, falls, or bounces. These are common on cliffs, mountain slopes, or riverbanks, and the size is very variable from a few blocks to thousands of meters cubed. Then we have topple on the top right. This is characterized by a forward rotation of a unit of material. The axis of movement is below the center of gravity. It's common in columnar-jointed volcanic rocks, cliffs, and stream banks. If we move down a row to slide, this is a downslope movement on a defined surface of rupture or shear surface. And there are 2 main types: rotational, which we see here, where the surface of rupture is curved upward, and translational slides, which have a planar shear surface with little rotation or tilting compared to the rotational slide. Translational slides can be quite ubiquitous in the environment and occur widely in a whole range of materials and settings. Then we have flows. A flow resembles a viscous fluid with shear surfaces very short-lived or not present. There's a gradation of slide to flow with increasing water content and mobility. They occur on steep slopes in gullies and around the world and can comprise rock fragments, granular material or mixes of debris and water. And then we have our bottom type, which is spread. Now, unlike some of the other types of landslides, these occur in gentle, flat terrain, generally with a stronger rock on top of a soil or weaker rock. It involves extension of the stronger rock, and often liquefaction is a cause. In this classification scheme by Varnes, we've also added the type of material. This can add valuable information in our description if we specify rock fall or soil fall, and it gives more context and information for our user. Material is divided into bedrock, debris, which is less than 80% sand and finer, and earth, so more than 80% sand and finer. So we can now say whether our fall is a rock fall, debris fall, or an earth fall. Complex landslide has also been added at the bottom of this classification, and it involves two or more of the above landslide types combined together. So in this instance, they've given the example of a rock avalanche or an earth slump, earth flow. In this classification, velocity has been used rather than type of landslide. So we have on the left our rock landslides, and we have on the right the unconsolidated material landslides. Now, velocity is important when considering the impacts of a landslide and evaluating hazards. Our landslides range from 1 centimetre a year. Now, these are things like creep, which is in the flow category, and we also have earth flow and slumps, to our moderate velocity landslides. These are 1 kilometre an hour with a high water content, so debris flows and mud flows, and also rock slides. And then we have, and debris slides, and then we have our fast landslides, so that's 5 kilometres an hour or more with a high air content. So these are rock avalanches, rock falls, and debris avalanches. In this classification, the activity of the landslide is shown. So active is straightforward, the landslide is currently moving, whereas a suspended landslide has moved in the last 12 months, but is not currently active. A reactivated landslide are those that are active, but had previously been inactive. So we can see in the reactivated landslide, we have our block that's fallen down into the river or into the sea from the bluff, and then we have a reactivation, another block falling on top of it. Then we move into our inactive category, so our inactive slides haven't moved in the last 12 months. Now they can be dormant, so inactive, but could be reactivated by the original cause. So here we have our block of material that's fallen into the water. Now if this was eroded away, then we could see how the landslide could be reactivated again. Then we have abandoned, so this is no longer affected by the original cause, so maybe water levels have changed and it's no longer being undercut. Then we have stabilised landslides. Now these have been protected by remedial measures, so they might have been pinned or tow protection might have been added. And then we have relic. So these are inactive and they've developed under different geomorphological or climatic conditions, and you can see how this one's been revegetated by trees and with a much more subdued topography. We have many of this type of relic landslides in the UK that were active during the Quaternary when climatic conditions were very different. Okay, so a couple of pictures here of actual landslides that have happened in Nepal. So I've started off with rainfall triggered landslides. These happened in the monsoon. These are on obviously very steep slopes in more unconsolidated material. And we're looking at shallow landslides, debris flows and debris slides. And these have been both confined within channels and gullies, which you can see, but also open slope failures as well. In this slide, we're looking at failures in rock, and these have been triggered by earthquakes. So we have rock falls on the left, so we can see all the individual blocks, varying different sizes, that have fallen down or rolled or bounced onto this road and damaged these cars and the houses. And then on the right-hand side, we have a rock slide which has blocked a river. Just like in the previous slide, this landslide has blocked the river. This is the Sunkoshi landslide, which occurred in August 2014. And what I put this in for is I wanted to highlight the fact that sometimes an event can lead to a cascade of hazards. So in this case, heavy rain or an earthquake can trigger a landslide, which dams a river, which when breached leads to an inundation of downstream areas. This is to highlight the fact that it's not always possible to study landslides in isolation. We'll need to consider what triggers the event and also the consequences. We're moving on now to what causes landslides. Now, ultimately, that's gravity. All slopes are under stress, and within the slope there are forces promoting movement downslope and opposing forces resisting that movement. If the resisting forces are greater, then the slope is stable. If the destabilizing forces are greater, the movement will take place. Let's imagine a block of material, like in the diagram, resting on a slope, which gravity is acting on. Normal stress is pushing the block into the hillside and resisting movement downslope. Shear stress is acting to push the block down the hill. The greater the normal stress, the greater the frictional resistance. The greater the stress parallel to the slope, the greater the shear stress. In this example, the angle of the slope increases in the right-hand side of the diagram, thus increasing the shear stress. Once this overcomes the normal stress, movement occurs. The forces resisting movement are grouped together as shear strength, which includes frictional resistance and cohesion. These two factors are affected by soil, rock type, weathering, presence of weak surfaces, and pore pressures within the slope. We use the term factor of safety to express the balance of resisting and driving forces. Shear strength divided by shear stress gives us the factor of safety. Factor of safety of more than 1 and the slope is stable, less than 1 and the slope is unstable, and factor of safety will be 1 at the point of failure. Factor of safety can vary over time. So what are the actual processes that can cause a landslide? Now these can be divided in a number of ways. We think first about factors that precondition a slope to failure. These influence the inherent stability of a slope. So examples would be a very weak plastic geological material making up the slope. There are then the preparatory factors that reduce stability over time, so an eroding river or vegetation removal. These are tipping the balance towards the driving forces, but it's not enough yet to trigger the failure. Then we have the triggering events, so heavy rain or a strong earthquake. These initiate failure. Tazagi differentiated between internal changes that reduce the shear strength and external causes that increase the shear stress. Often, a slide will have multiple causes, but only one trigger. When considering these different causes, it's useful to think of our slope in one of 3 different states: stable, marginally stable, and actively unstable. So imagine a stable slope is intact, strong rock at a relatively low angle. It's unlikely a trigger, such as an earthquake or heavy rain, will initiate failure. If this slope was a bit steeper though, and the rock slightly weaker with more discontinuities, it's easier to imagine how a trigger that's big enough could initiate a failure, and the slope would become actively unstable. So now we're going to have a look at this graph here, which is imagining a slope over time, and it uses factor of safety to track the change in state. Our slope is stable, but it's gradually reducing the factor of safety due to weathering. Heavy rainfall leads to a drop in the factor of safety, but this is then recovered when the slope dries out. Our slope is still stable. Now imagine an intense erosion event which leads to a big drop in the factor of safety. This is considered our preparatory factor. The Working Party of the World Landslide Inventory grouped causes into those that were ground conditions, geomorphological processes, physical processes, and anthropogenic processes. In this slide, I've highlighted the preconditioning factors in red, all of which fall under ground conditions. These factors in red are preparatory factors, so there are erosion, our deposition, our vegetation removal, and excavation. Earthquake can be both a preparatory and a trigger. Some factors can also be preconditioning and preparatory factors. So slope, for example, is a preconditioning factor for all landslides, but a change in slope, for erosion by example, is considered a preparatory cause. Those factors shown now in red are our triggers, and these are the ones which actually start the movement of the landslide happening. So we're looking at things like intense rainfalls, snowmelt, or earthquakes. So the earthquake increasing the shear stress of the slope. I'm now going to focus on two triggers that are important to the meteor work. The first is rainfall-triggered landslides. Triggering rainfall can take different forms: intense short-duration events or periods of prolonged rainfall, such as during the monsoon. In soils, the type of landslide triggered by rainfall can be influenced by these characteristics of intensity and duration. Shallow slides and flows triggered by shorter duration intense events often, and larger deeper seated failures which require a build-up of antecedent rainfall. During a storm, rainfall rapidly infiltrates this slope, leading to a saturation of the soil and a temporary rise in pore water pressure, which can trigger the shallow landslides. The water in the slope acts to oppose normal stress, our resisting force, and reduces the effective normal stress of the slope. Water also increases the mass of material on the slope and, in turn, the gravitational pull. We've seen evidence for intense rainfall triggering debris flows in materials with high permeability in the sub-Himalayan zone of western Nepal. Next, we'll look briefly at earthquake-triggered landslides. So earthquake-induced landslides can occur due to ground shaking, liquefaction, or shaking-induced dilation of sediment, which allows rapid infiltration of water. Earthquakes trigger different styles of movement, but it's predominantly falls, soil slides and rock slides. And we also saw different types of landslides for different slope angles, so rock falls or soil or rock slides for steeper slopes, and earth spreads and slumps triggered on gentler slopes. The intensity of earthquake-triggered landslides depends on the magnitude of the earthquake. So the higher the magnitude, the greater the landslide intensity it may trigger. Studies also suggest that most landslides are triggered by earthquakes of a moderate to high magnitude, and that most of these landslides do not occur beyond a certain distance from the source of the earthquake. Moving on from what causes landslides to how we record them. So a landslide inventory map captures the location of landslides in a study area. Now, it can either be a point, usually recorded at the highest point of the landslide on the backscale, or a polygon depicting the outline of the whole landslide mass. So ideally, you want to capture extra information rather than just the location. So you might want the date, the activity state, and also the type of landslide. Numerous ways exist to create a landslide inventory, and the techniques used will be dependent on the scale of the study area and its subsequent use. Techniques commonly used include stereo air photo mapping, satellite image interpretation, which are obviously suited to capturing the outline of events over larger areas, as well as direct field mapping, which is obviously suited to a smaller study area unless there is considerable resource available. We've also seen a rise in the use of social media, citizen science, and harvesting of news reports. Now, these can offer information if you want to keep updating an inventory without direct mapping, or if you don't have access to multi-temporal imagery. Some authors differentiate the style of inventory based on how the events have been mapped. So an archive inventory, as you would expect, have been produced through searches of archives, such as reports, newspapers, and journals. Geomorphological inventories have been created using direct mapping techniques and capture events either historically, so all landslides regardless of age, or they can capture events associated with a monsoon or a single trigger event like an earthquake. Brad defined multiple uses for inventory maps, which I will flag up before focusing on susceptibility maps. So inventory maps can provide valuable information on the distribution, type and pattern of landslides in an area, which is really useful information for planning purposes or for civil contingency. Inventories form part of the study of the evolution of an area by mass wasting and are a preliminary first step towards susceptibility, hazard and risk assessment. So landslide susceptibility here is defined as a quantitative or qualitative assessment of the spatial distribution of landslides which exist or potentially may occur in an area. Susceptibility shows the likelihood of an area being subject to landslides, sometimes described as the spatial probability. It gives us the where for hazard assessment, but not the when or the magnitude of future failures. And it can be expressed qualitatively, so high, medium, moderate, low susceptibility, or quantitatively. So our susceptibility takes our inventory map and it moves it a step on and it expands it to fill in the gaps and depict areas where landslides could occur but either haven't been mapped yet or haven't occurred yet. Susceptibility is determined by correlating the predisposing factors of an area, such as geology, slope, elevation, distance to roads, with the inventory of past events. It's therefore important, if you're using an inventory to create a susceptibility map, to have a detailed and spatially representative inventory. Landslide susceptibility mapping is founded on the principle the past is the key to the present, and it assumes a level of static conditions. If there is active quarrying, forestry, or road building, or even climate change, this can have an impact on the susceptibility map and should be taken into account. There are various techniques for producing a landslide susceptibility map, and there is a wealth of scientific literature on this matter. What I've tried to do here is separate the methods into qualitative and quantitative, so the different types, they're in the blue circles, and then all around them are some of the things that you need to take into account when deciding on the technique that you will use in your study. So your chosen technique will be influenced by the size of your study area. So are you looking at a national scale study, or is it regional, local or site? Now all of those will need to be taken into account when you're choosing your methodology, because not all of these different methods are suitable to be used at every single scale. You also want to look at the type of landslide that you're looking at. So do you need to look at the initiation of the landslide as well as the run out? So will you need to look at both of those in your susceptibility? You also need to look at the objectives of the study. Do you require a level of objectivity about the results? And also, how complex is the study area and how variable are the factors and how do they change spatially? So if there's not a lot of spatial variability, this will be less useful for some of the statistical methods that can be used. Data availability also plays a significant role, as some of the techniques are data intensive. Resource availability, such as computing power and time, are also a factor in considering what method you will be choosing. So if we have a look now at the qualitative methods, we have heuristics, so index-based, and geomorphological mapping. Heuristic methods rely on the expert assigning weights to mathematic data, which reflects their knowledge of an area and of a process. It's quite a high level of subjectivity in both of these methods. In geomorphological mapping, the susceptibility is assigned directly based on geomorphological evidence of instability features. In our quantitative methods, these are less subjective and they involve less reliance on expert judgment and are based more on the data. Deterministic approaches model the process and can be very data intensive, requiring a lot of input data on geotechnical and hydrological properties, and they often use slope stability software. In statistical approaches, a combination of landslide occurrence and predisposing factors is carried out statistically. This can be used either bivariate or multivariate statistical techniques. Analysis of inventories can be carried out through creation of landslide density maps, for instance. As well as an inventory of landslides and a detailed knowledge of your area and also the landslide types and processes that are occurring, it's also necessary to have thematic data to input into your susceptibility model. There is a tendency to use any data which can be generated or gathered, and it's important that the data that you choose is relevant to your study area and also to your landslides. In a review by Reichenbach, all of the thematic data which had been used in susceptibility models published in the literature were looked at and analysed, and it's grouped together in this grid that I've put on this slide. Now, the thematic data was grouped by 5 different types: geological, hydrological, land cover, morphological, and other different types. This really gives you a feel for the diversity of factors which have been included in many susceptibility maps, but also the common themes and the common landslide thematic data which has been used. So we can see here that slope and geological, lithological factors are by far the most common, as you would expect, and then also we have things like aspect, land cover, curvature, elevation as well.